Today I'm just going to go through the first intro of networking, SAN and network storage. I'm going to call it network storage NS because there's so many different ways of doing it. You'll pick your own route, I'm sure. So in the background on my screen and displaying in the main picture there is this information here. Okay, so you've got your hard drive, 480 to 800 megabits per second, and I'm including hard drives and SSDs in that. Now I give that specifically because we have to go over to the bus speed. So basically what I've shown in this slide is the hard drive speed, your SSD speed, your M.2 drive speed, and your network card has a great big question mark over it. Now the reason why there's a big question mark over it is because your network speed will only go as far on storage as your storage is fast. So this runs on, and I'm hoping, because I did this yesterday, so let's say we got 3 hard drives running in RAID. They're 800 megabits. We're not going down the route that there are hard drives. We're just going to go your storage solution, okay? So your storage solution does 800 megabits per second. So if we put 3 of those together, we can get 1.4 gigabits per second. And those gigabits, so if I had 12 drives, I can go up to 5.6 gigabits per second. Now that's great, and this works with topology. Now if you have a PCI Express 2 motherboard, you can actually run the full speed of 12 drives on your PCI Express motherboard. You cannot exceed the PCI Express speed across your data throughput. So if you had a 6 or 8 gig LAN card here, then with 12 drives you're perfectly fine, you're within your overhead. So 10 gigabits is 1250 megabytes per second, just so that we're really clear on what bits, bytes and all the other terminology that's all mixed across the networks by their device type, so that you get the right information. So your bus speed, so here look, I've done exactly the same thing. I've given it 1200 megabits per second. Now depending on how or what you buy will really give you that speed. So you've got your sequential write speed, which is going to be your biggest speed, and then probably half of that's going to be your actual real world speeds that you're going to get. So this is 1200 times 3 is 3.75 gigabits from the 3 drives, and 12 drives here are 15 gigabits. So what you need to do then is just to do the math. So that would be a 20 gig card would max out your 12 M.2 drives as PCI Express 3 standard. All the average card is now on PCI Express 3. So you're going up then straight up to your 20 gig card, because there's raw data and there's actual data. So you need to go above your actual raw data speed. It won't, because there's a 20% overhead, so literally it's whatever you've got minus 20%. So what you need to do is think about how this actually applies. Your drive speed to your controller it will dictate to the server's hardware, so your motherboard, then which dictates your LAN speed. So if you have 1 megabyte from there and 0.5 megabyte, half a megabyte there, then the only speed you're going to get across there is less than 0.5 megabytes. So if we look at it this way as well, your PCI Express in your server, will dictate the maximum speed you can get on your controller card, and then so your controller card can't exceed the speeds that your drive. So your drives can match the speed of the controller card, but your controller card will match the speed of your motherboard, and the whole lot goes together and makes your LAN. So I hope that's somewhat near clear. But you don't want a bottleneck, because if you've got really high speed here but your server's slow, then everything's going to literally just dump onto your server. You'll get high CPU usage and high RAM usage, because there's nowhere for the drive data to go from the network once it arrives at the server to your drive. It will just literally go here to here and then trickle through there. So you'll get a real big issue there. And I'll show you some demonstrations of that occurring. So to understand PCI Express and processing power, you normally get this kind of information from the website or wherever you're going for your processor. So if you look, it gives you, it's 4 point. Let's look at this, the i7-10710. So you can see it does DDR266. It has a graphics frequency, all-core turbo, its power supply, whether it's got integrated graphics in its cache. Well, none of that information is really helpful at all. Your processor speed in gigahertz and what they actually process is like literally like 1.2 gigs of data every second. So but your storage array can process, and that's a separate system. I think people think that their computer and the hard drives they have in their computer are one and the same. They're completely not. Your drive speeds can be completely different, and scale is more scalable obviously than your processors. And I'm sure that some of you will know already that you have dual processors in there, and that kind of ups your speed. It doesn't give you double the speed, but it ups your speed on your compute. So there is that difference there. So what we've got is, I've put on the bottom of here is the giga transfers a second, and that's how processors are measured. Now giga transfers are 10-bit instructions. 8 of that is data and 2 of that is clock cycle and overhead information. That's why you get your 20% off. So these are PCI Express buses here, and the maths on there. So you can get 125.44 gigabits per second as a standard for PCI Express 3. And then 32 gigs as 2, and 63 and 63.1 as 2. So your gigabits per second, that's bits, not bytes, not megabytes, nothing like that. So you have to do the maths from there. So if we're transferring 125.44 gigabits, and I think we do some maths on here. So this is the information. So the doubling of speed was through the generations of the PCI Express, which is your main system data transfer internally, how quick your motherboard would work. So back in the days when PCI Express first came out, Gen 1 and then Gen 1.1, you could get bi-directional channels. Now you've got to think of your data connection, and the transfer of data is always bi-directional. It's always two-way. So basically I go, right, let's say you're my hard drive. I want to save this data, which is this pen. Do you want the pen? Your answer is yes. I give you the pen. That's another transaction. And then have you got the pen is the third transaction. And so that answer that you didn't give me, because you're only watching a video, is the data that's received from the data flow across your network. And there are other things in there as well. It's like, what size was that supposed to be? What size is the pen? What color is the pen? And those data is also transferred. So you used to be able to get 5 gigabits per second, and all the processors were rated for this 5 gigabits per second. So, but that's shared, so it's not parallel, it's serial connected. So out of there you would have, say, your hard drive, and then you'd have your graphics card, and then you have your memory, and all of that literally shares that bandwidth, and all those communications have to go to, you know, talk to each other, and that's where you get the difference with using the older processor architecture on older motherboards, that they were always that much slower. So when we get to 16 lane PCI, but 16 lanes, or 16 times, you can get up to 80 gigabits per second. Now this is the difference between the laning. So what you do is you've got 60 gigabits or 64 gigabits of unencoded information. So when you took that down, it worked out something like 63.1 gigabits on those 16 lanes. So we're referring really to raw data, the number of megabits that the bus can move or transfer. So encoding process is going to reduce the bus down to probably 80% anyway, just on overheads, but that's obviously a completely shared system. So on this PCI Express, we actually see the actual data in terms that we're probably more familiar with. Now here we go. So PCI Express 2.5 gigahertz transfers, which would give you at one times would be 250 megabytes. So when you had SATA, and you had SATA 1, you had 150, which would give you your overheads there. So then we went on to SATA PCI Express version 2, which was our 6 gigabits per second. And what we do is, if you look at the multipliers here, you can see where that sits. So PCI Express 1 16 times multiples were only giving you 4 gigabits per second, which isn't a great deal of information whatsoever. So we're now at the cusp of SATA 4 coming out. It was introduced in 2017, and it's like been held back. So people are like, you know, SATA 4 isn't compatible. It's not in the motherboard, so the processors can't actually do it. They don't do a lot of processors. In fact, they are quite slow. So even though it's supposed to be introduced, and we are now in 2020. We're going to get these kind of speeds here. So we've got 16 gig transfers per second, which is just under 2,000 megabytes per second. So that really does give you the inside of the data. So these are all raw data. Obviously, we have to take 20% off them. So when you have your M.2 drive and it's reading about 1.7 megabytes per second, then you can understand now why it's running that speed. It's supposed to be about 4 times, so that's 7.8 gigabits per second. Let me just open Internet Explorer. I'm just going to pause it and just double check that figure for you. Yeah, so I quickly checked that. That's 985 megabytes per second here at 8 times on PCI Express 3. That's 980 megabytes. That's not a huge, great big deal of documentation or evidence or data. You know, we're talking, well, that's just slightly more than a, this is a CD, these are 720 megs. So, you know, these are, so one of these every second, which is technically, it's quite a lot of data in old school terms. However, when you look at the size of files these days, it's not. You would, and I would want a 4 gigabyte per second channel transfer. That brings you down to, you know, your DVD size of data, and of course it speeds everything up. So this is supposed to be doubling and doubling and doubling and doubling. So, you know, you're going to get, you know, by about PCI Express 8 or 9 you're going to get a decent high speed for modern use, but hard drives and data transfer has always lagged really far behind. So on here I've done it, so a PCI Express 4 Gen 4 at 16 speed does 3150 megabytes per second, and because most cards are a 4-speed card, we have to kind of like look at that sort of speed, and people are going to probably recognize the 787.5 megabytes per second transfer rates from if you've benched your drives, and I'm sure if you're watching this you probably have benched your drive using Crystal Mark or something and saw the speeds or not, as the case may be. So that's kind of like your averaging speed. So let's have a look at how the processor affects this, because obviously they have to process the data. So as you can see, this is the i9-9900 KS processor. It's one of the fast processors. It supports PCI Express up to 16. 2 8s are 16 and 1 8 and 2 4s are 16 as well. So you get your maximum speed of your processor. So on here I've literally left it what is the maximum data of your processor, and it can transfer 3150 megabytes per second. That's it. So if you have that processor there, that's all you're going to get. You won't get any more performance than 3150 megabytes. And if you look at some of the M.2 benchmarks where people are benchmarking the hard drives, you'll see that they get quite close to this. It's like 2900 megabytes or something like that, because the more you use your system to do other things like display graphics, the more that bandwidth is used up, and thus you get your slower speed. So technically this is megabytes, so your fastest network speed that you could use theoretically on a single core system, one motherboard, PCI Express 4, is going to be 25 gigabits per second. So if you had 40 gigabits per second, you'd have an overhead there, but that's a 1-to-1 ratio, so that's not entirely good theoretical practice. However, that is probably the best way to explain it, is that once you get, if you've got one motherboard with one processor, you're going to get that speed, and it doesn't matter how many times you try to get faster than that, you physically cannot, because your hardware won't let you. So that's doing what I would call doing a Linus, of dumping in so many drives in there that you couldn't possibly get any faster speeds. The only way of doing it is to load balance and cross server. So what you do is you have 2 storage arrays feeding into one that's on a load balancer, which will slow you down anyway, and that's how you do it. But you can use dual sessions to do it. I've done dual sessions quite a lot just to really get the high speed connections that I want. So a dual session is rather simple. High speed connection, then you need to be looking at the Threadripper cores and that kind of thing, because they have up to, I think the Threadripper has something like 60 PCI Express lanes, so you can have multiple data arrays on your system and feed them through your PCI Express lanes. So don't forget, this is at 16, so you know you can have 4 times, we're going to say 4 times as much data throughput here on a card. So if you've got a card, sorry for the reflectiveness, so if you've got a card there using 16 speed, that can do 3100 megabits per second, and if I have another one, that will do 3150 megabytes as well. So that would give me double the total across those 216 lanes. So once we've gone across those 216 lanes, then we need to be able to push that across our network card. So I'm going to have 2 of these cards, then I'm going to have 2 network cards. That's 4 PCI Express slots taking up, and I need them to be high speed. So let's go back here. Well, if I'm doing 16 speed, well, and I need 4 cards, well, Intel's just told me, what can it do at 4? It can do 2 at 4, so it can only do 2 network cards at 4 speed, which brings us down to the, you know, the 1000, right here, there we go, 787.5 megabytes per second. So then I've reduced my speed down because there is nothing on my computer, no hardware that will do it. So what you're looking at is 2 16 slots. So normally people use those for their graphics cards, so it's not uncommon to get 1 or 2 16 speed ports or PCI Express ports on your card. However, trying to get a PCI Express 16 speed LAN and data cards are going to be probably more problematic. You'll probably get the 4 speed ones, PCI Express times 4, you'll probably get those. So that's your maximum speed on how you connect into your drives. You know, you're creating a bottleneck there. So if you had one PCI Express 16 card and another PCI Express 16 card, one doing the storage, one doing the LAN, then you kind of have your 1-to-1 ratio there, provided you build your drives up to meet that specification and you minus your overheads. Now I'm pretty sure I've done this to minus the overheads as well, so that it's a more realistic figure that you're working with. So, you know, between 787 megabytes per second to 3115 megabytes per second is really your max speed. You can double it over, however, you know, it's how you set it up and what your motherboard manufacturer offers you. I'm just going to have a quick look and see if I can find a TXR 40 board with more than 4 PCI Express 16 slots, and we'll see how that actually works. What I've done is I quickly looked up Asus, because Asus usually are the ones that try and get everything in on their boards. So this is kind of your domestic market process, a motherboard. Now you'll probably end up having to go to a server board. Now server boards are more robust, they're designed for this type of application, whereas domestic boards kind of one size fits all. So in here I've looked it up and we get 2 16 slots and then 2 PCI Express 16 slots that run at 8 speed. So that's, let's have it. That's really good, thanks for not being helpful. Can we get it any bigger? No. So 16, 16, 8 and 8. So we do lose speed, but you know, it's just a matter of which way do we do it. Do we have a dual LAN and dual system? Now I'd go probably down the dual system, so I'd have one high speed, ultra high speed, so a controller card and a network card, a controller card and a network card. So there is no uncertain terms here used that this will have to have a VMware type operating system. So you would have a dual operating system just like any other server on there, which would isolate the two networks completely from each other. So yes, put a VMware on there, whatever your choice is. I like using Proxmox, by the way. I've used ESX or whatever it's called. I've tried Zen Server, and I've gone through quite a few of the different types of operating systems, you know, hardware operating. And you know, Proxmox comes up and it does actually work quite well. You know, if you go down load balancing and you have two hardware routes going into one router, you know, that router still has to cope with that data flow, and you're still only going down to one computer anyway. But if you're going to do it one-to-one, then you don't have your backups and redundancies, nor do you have probably an archive. So you must configure having an archive as well, which is why we put in the Ethernet cards, because there's no point in having, you know, you're going to upgrade because you've probably got storage already. So what you want is your NAS over Ethernet as an archive, and literally just go and switch it on and get it to do weekly, monthly timestamps or whatever, whichever way you want to run your policy procedures for data back. Probably going to be covering the specification of what is your network and system storage maximum data throughput. The answer is being given to you. Your maximum speed at current tech is 3,000 or 4,000 megabytes. What was it? Anyway, and should calculate your network for you. This chart's probably going to be your best chart for actually working out what you can do, because it literally gives you the gigabits on there, so you can work it out. All you do is just minus 20% off the figures that are given, although that looks actually quite right, and that will give you your speed of your network and your hardware, and you can do your maths accordingly. So don't exceed your maximum performance, because all you're going to do is end up creating a bottleneck. Okay, I just quickly wanted to go through the two pictures that I'm going to show now, which are the bottleneck network pictures. On the first one, what we're doing here is a upload-download test across networks. Now the difference here, as you'll see, is on this one, which is a upload bottleneck. The hard drive on here is a single drive, and it's slower than the network can actually cope. So what it does is it takes the files and takes them from the drive, slowly it caches them on the RAM, then it sends them over the network. Then there's a packet, the network then receives them at the other end, and this is what you're seeing, and it then writes that file that it got in all that data to the thing and goes, right, can I have the next one now? And then it gets to a queuing point, and all those little troughs in this picture shows the obviously if you look, you've got the network and then you have the hard drive performance, and you'll see that the network goes along and stops whilst the system then takes it from cache to write it to its own drives. Now in this other picture we have the opposite, where we have a 1-to-1 ratio. So on here you can see there's no peaks and troughs all the way along. The data flow and the network flow is very similar. Unfortunately I couldn't show you the full speed from both systems in both the same format, but what we did is we were using 13% of the drive speed on the receive on this one. So this is actually coming from the exact same hardware. So I uploaded to the server using a hardware configuration, and then downloaded using a different hardware configuration, and this is the difference. And I can tell you this, that doing 20 gig transfers to get outside of buffer is a long and laborious test to actually run. This is actually, I think it was 26 gigs or something like that of you know, gigabytes, not bits. And literally it was just trying to work out where the bottleneck was. Now it used to be, you know, the thing that I used to have to do constantly when I worked for various companies. So is to look at where their bottleneck is and why, or where there is a differentiation between the predicted or theoreticals to the actual, you know, reality of things. So it's a difference from what we think to reality. So yeah, so you can't get, as you can see on this one, any part of the system which slows down, including your routers, will cause or create a RAM surge and a processor surge and an overload, because it's not moving seamlessly through the network, and it should go, you know, without any hiccups, a 1-to-1 ratio. That's, you know, you can't have a 2-to-1 ratio, because the 2-to-1, as soon as it goes from the 2 to the 1, will cause problems and slow you down. So you can't do that. And even if when you start considering load balance and things like that, if you build a network to run for 5 users and it's all 1-to-1 ratio, once you go through and you're going, there's only 2 users on there, then you start having a bottleneck at the server end or routing or networking end, and this can actually be more detrimental to the network's performance. It doesn't scale very well in reality. So yes, trying to kind of like match everything is really a pain in the neck. most of the time, and yeah, I really enjoy it. Okay, so thanks for watching. I'm sorry if you fell asleep watching this video. They can be quite boring when we look at sort of like technical stuff. I'm sure you're just on